So by now, we should understand that there's some really weird things that happen when we start moving close to the speed of light. So let's do a bit of a thought experiment here. Let's say we have two spaceships, right? One is parked beside us, moving 0 meters per second, relative to us. And one is flying by Earth. And we're able to see this rocket that's flying incredibly fast by Earth. And it's moving at 1 times 10 to the 8th meters per second, which you might recognize as a third of the speed of light. The speed of light is 3 times 10 to the 8 meters per second, right? So this one's moving very fast, a good proportion of the speed of light, and this one is at rest. Well, how would these two rockets appear to us from an outsider point of view? And what will the differences between those two rockets be? So let's start off, we're going to look at this in terms of three things: time interval dilation, length contraction, and momentum, how momentum seems to differ. And let's start with length contraction, because that's, I think, the simplest one. So we have this rocket beside us, and let's say it's 100 meters tall, right? It's sitting there, it's 100 meters tall. No biggie, we can go walk right up to it and measure that's 100 meters tall. But this same rocket, if it's flying by us at a big portion of the speed of light, a third of the speed of light, it's going to actually appear as if it is shorter, which is sort of strange. So it's like the whole thing has sort of been compressed. It hasn't actually been compressed. It's just how we observe it to look is a little bit shorter. And if we were to measure the length of that fast-moving rocket from our outside perspective, like we were magically able to hold a ruler up to it as it's flying by very fast, we would actually measure that it only has about 94 meters in length. So it looks to us like it's sort of shrunk by 6 meters. It's 94% of the original length, which is sort of strange. Now, the people on that rocket wouldn't feel compressed or anything like that, because remember, everything is relative. So this is just how we observe them. And in fact, they would observe us the same way. So if they were seeing us on the ground as they fly by, if you usually have a height of 1 meter, you're gonna, to them, right, if you measured yourself, you would measure 1 meter, but to them, moving very fast by you, you would actually only have a height of about 94 centimeters. You would be shrunk by sort of the same percentage that they observe. So that's what length contraction is. And the way you calculate it is the length of the moving object, so in this case, this rocket here, from our point of view, is equal to the length as if that same rocket were stationary divided by this thing. And that thing, that symbol, is called, well, it's a Greek letter, and it's just a gamma. And it looks sort of like a G, right? It is actually the Greek letter G, but it doesn't have the loop at the top. So it sort of looks like a cursive G without the loop at the top. So it's just the stationary length divided by a factor G. And G is called the Lorentz factor, which is related to how fast you're moving. And we'll learn how to calculate. It's not very difficult to calculate, but we'll learn how to calculate on the next page. For now, just assume it's some number that multiplies or divides by these things. In this case, actually, in this example, just to let you know, the gamma factor that I calculated, the Lorentz factor, in this problem, moving at 1 times 10 to the 8 meters per second, is about 1.06. Okay? So basically, to find the length of the stationary object, we just divided the length 100 meters divided by 1.06 is how we got the 0.94, or the 94 meters. So let's talk about time dilation. So dilation is the opposite of contraction. Contraction means when something gets shorter or smaller. Dilation means when something spreads out or gets larger. Like you might have heard of your pupil dilating. And what that means is when your pupil gets larger in the dark, for example. So what time interval dilation means is how the interval of time gets sort of spread out or long on something that's sort of fast moving compared to us. So let's start off super simple. If we take a clock, right, and we look at a clock on, say we can see through this window, right, and we look at a clock on that spaceship, and on our clock, so on our wrist, so this is the spaceship's clock, our clock, this is us, observers down here, If we were to start our clock in sync with that clock, and we were to time how long the 15 seconds would take, so we time basically how long it would take the second hand to go from here to here, how long would that take in our clock? I mean, shouldn't it just take 15 seconds? Yeah, it should, right? Because the thing's not moving to us. It's just looking at our clock and looking at the clock on the spaceship is going to be the same because they're not moving relative to each other. But the weird thing starts happening when we start to look at the clock on the spaceship. So let's say we're able to magically see into the window of this spaceship that's moving very, very fast, right? And when their clock gets to the top, when the second hand gets to the top, again, this is us down here observing, right? When their second hand gets to the top, we start our second hand at the same time, right? And the question is, watching their clock, how long would it take their clock from our point of view to reach the 15-second mark? And you might think 15 seconds, but it actually doesn't. This is another strange case with relativity. And you might have heard of this, that time slows down when you reach the speed of light. And that's sort of true. It's true from our view looking onto this spaceship. So it would actually take, so if we were to see this clock go from here to here, on our time, on the wristwatch that we have, it would actually take a little bit longer. So it would take 16 seconds, approximately 16 seconds for our clock, for the clock on the spaceship to appear as if 15 seconds has gone by. So that's sort of strange. Basically, the time, each second on the spaceship has taken slightly longer than a second, right? So time has gone a little bit slower. So if you were to see into that spaceship, it's sort of like everything would be moving in slightly slow motion from our point of view. Now, the weird thing is, if you were to flip the situation around and you were one of the people on that spaceship looking at us, it's like they're moving, the people on the ground are moving at this speed relative to us, so they would appear us on the ground to be moving in slow motion as well. We would basically be witnessing each other moving in slow motion, and from their point of view, they're just moving at normal speed. So, very strange thing. For now, let's just look at the calculation. So, we have this stationary time here, which is multiplied by our gamma factor, which again in this case is 1.06, and that's going to give us our moving time. And the time here, be very careful, what it represents is a time interval. So in other words, the distance between, or the amount of time between two events happening. In this case, the example that we're using, it's the event between starting the stopwatch and stopping the stopwatch, right? So what happens if they're looking at the clock on their spaceship, stationary, so the clock is stationary relative to them, it looks like 15 seconds have gone by. But from an outside observer, us, right, witnessing this moving clock, it's going to appear as the 15 seconds times the gamma factor, which is how I got that approximate 16 seconds. So again, this is, if you're looking at the clock from a stationary point of view, the clock is beside you, so the people on the spaceship looking at the clock, 15 seconds have passed. But from our point of view, that same interval has taken 16 seconds of our time observing the moving clock. Okay? The last one here is momentum. And this one's pretty straightforward as well. It's all you're going to do is you're going to take the momentum that this stationary spaceship would have, multiply it by the gamma factor, and that would tell us how much momentum the moving object has. So two objects, if they're moving at different speeds relative to us, actually have different momentums. But if you remember, how do we calculate momentum? Well, momentum, isn't that just mass times speed, right? So of course these two objects are going to have different momentums, right? Because they're moving at different speeds. But the strange thing here is that it's not just mass times speed or mass times velocity. It's actually mass times velocity of the stationary object times the gamma factor. So it is a little bit different, and we'll see that with an example below. So I actually want you to try these 3 parts to example 1 yourself. Pause the video here, try them yourself. You're just going to use those 3 equations. I tell you what the Lorentz factor is here for this question. It's 2, which means, yeah, in all these equations, the gamma thing is just 2. So see if you can figure them out. Unpause the video when you're ready and I will reveal the answers. So here are the answers. So the length would seem to contract by a factor of 2. So the spaceship would seem to be 20 meters long. Looking at a clock, from their point of view on the spaceship, 10 minutes will have gone by. But from our outside perspective, looking at that clock or timing that clock's 10 minutes, it would actually take 20 minutes of our time for their clock to go by 10 minutes. That's time dilation. And then the relativistic momentum. Now, I didn't actually finish this one because all I did was I calculated the momentum of the spacecraft, which came out to 1.56 times 10 to the 13 kilogram meters per second. But the weird thing is, even though it's moving at a speed already, this actually isn't the relativistic momentum. This is just the regular momentum. And I know it's called stationary momentum. I've called it stationary momentum. But that's just the momentum that it would have from their point of view, right? So the people on the rocket, if they were on a spacecraft and they saw that they were moving at this speed, they would calculate their momentum as this value. But from our point of view, outside of the rocket, observing them from the outside, we would actually see that their momentum was this times gamma. So it actually would be twice this much. So it would be approximately, well, what is that times 2? It should just be around 3. Yeah, 3 times 10, 3.12 times 10 to the 13 kilogram meters per second. Which is sort of interesting because, yeah, like momentum already takes into account speed, but it doesn't take into account relativistic speed. We have to use the gamma for that. So now you might be wondering how we actually calculate this gamma factor, this Lorentz factor. And this is the equation for it. It might look complicated, but it's actually not that bad, right? We're just going to do 1 divided by the square root of 1 minus v squared over c squared. So the only unknown in this whole equation is v, right? C, we know, is the speed of light in a vacuum, which is just 3 times 10 to the 8. So that's a known. We always know that. So the only real variable in this equation is v. So it just takes a little bit of calculation, but it's not so bad to calculate. So let's look at some examples. If an object is moving at 10 meters per second relative to us, so like a car is driving by at about 35 meters per second, kilometers per hour, that's about 10 meters per second. So what would the Lorentz factor be? So let's calculate it. Gamma equals, well, it's just going to be 1 over square root of 1 minus v squared over c squared, right? Which is just going to be 1 over the square root of 1 minus 10 squared over 3 times 10 to the 8 squared, right? And don't forget to square that 3 times 10 to the 8. That's a very common mistake here. What do we get? Well, just in case you're having a little bit of trouble plugging this into your calculator, the way I usually start is I evaluate this part on the inside of the square root first. So in my calculator, I punch in 1 minus 10 squared over 3 times 10 to the 8 squared. And if I do that, interestingly enough, this thing in the denominator just becomes 1. So it just ends up being 1 over the square root of 1. Which, I mean, if you do that math, it just comes out to 1. So that's sort of interesting. So the gamma factor of 10 meters per second is just 1. What happens if you do the same thing for 1,000 meters per second? What do you get? So now the object is moving faster compared to us. Like 1,000 meters per second is a kilometer per second. That's very fast. That's faster than most things on Earth, right? Except for rockets and bullets and stuff like that. And if I do that calculation on my calculator, interestingly enough, this thing down here comes out to 1 again. My calculator just tells me it's 1. And the reality is, this thing over here, when it's calculating 1,000 squared over 3 times 10 to the 8 squared, it's basically 0, right? Because these speeds are so low compared to the speed of light that my calculator can't even handle all those decimals. It basically just tells us it's 1 again, right? So the first thing we should notice here is that when you're moving slow compared to the speed of light, the gamma factor is 1. Well, what happens if we start moving faster? So 0.1c refers to 10% of the speed of light, right? What is that gamma factor going to give us? Is it still going to be 1, or is it going to be a different number? Well, let's calculate it. So gamma equals 1 over the square root of 1 minus 0.1 c squared over c squared. And do a little bit of algebra here. You might notice that there's a c squared here and a c squared here, and they cancel out. But you got to still remember to square that 0.1. You got to square that whole thing, right? So the calculation actually becomes a lot simpler inside the brackets, right? Or inside the square root. It's going to be 1 minus 0.1 squared. And if you do that, you're going to get, oh, we actually get something slightly different from 1 here. We get 1 over the square root of 0.99, which gives us 1 over the square root of 0.99 gives us, okay, gamma equals 1.005. Okay, so we've gone up a little bit. Now we're moving at a reasonable amount to the speed of light, and our gamma factor is 1.005. So remember what this value is. This value tells us, if we go back to our first questions, how much length contraction or time dilation something would experience from our perspective if they're moving that fast. So even if you're moving at 10% of the speed of light, the length of an object will only contract by about 0.5%, right? 1.005 is only increasing or decreasing by 5% or 0.5%. So even this speed, it's barely just decreasing by a little bit the length. And that's why it makes sense that the gamma factor is basically 1 for slower speeds. So now I want you to calculate it. What's it going to be for 0.99c? What's the gamma factor going to be when we're traveling 99% the speed of light? So pause the video here, try it, and we'll talk about it. And if you calculated it properly, it should come out to 7.09. So now we got a number, right? A realistic number. So basically what it's saying is if you're traveling 99% of the speed of light, the length of the thing would contract by about 7 times. So it would be about a seventh its original length. Time dilation would be about 7 times as long. So timing 10 seconds would appear like 10 seconds on the clock on the spaceship from our outside point of view would take about 70 seconds for it to pass by. So sort of interesting, but you see it requires us to be going very fast to get bigger numbers of gamma. Now, the question is, what happens when you start plugging in value like c, right? What happens if you just plug c into this equation? Well, just looking up here, right, we're going to have c squared over c squared, right? And those are going to cancel out to give us 1. So in the denominator, we basically have 1 over the square root of 0. Well, what happens? We can't divide by 0, right? So this actually comes out to undefined. And I mean, the reason for that is because according to this physics and according to this relativity, we can never actually move at the speed of light. Basically, the math breaks down at that point, and it tells us, it hints at the fact that like no matter how much energy we put into something, we can never reach that speed. What happens if we try to plug in a number bigger than c into this calculation? Well, if you try to do the 1.1, right, you're going to do 1 minus 1.1 squared, basically, in the denominator. What you're going to end up with is, well, I can erase the 0. You're going to basically end up with 1 over the square root of negative 0.21. Is there a problem with that? Well, if you try plugging this into your calculator, you're also going to get error, right? Because you can't have a negative number under a square root. So again, this is also undefined, right? So we can't be at c, right? We can't plug c into this gamma factor, and we can't plug anything larger than c into this, because again, that's the whole principle that relativity is based on. It's based on the fact that the maximum, sort of the speed limit, the fastest that something can travel is approaching the speed of light. We can never actually reach the speed of light. So you'll notice the values of gamma basically start at 1, and in fact, if you plugged in a speed of 0, you would get exactly 1, right? But anything slow moving would be approximately 1, and that's why things that we observe in our everyday life don't really exhibit these relativistic effects, because the gamma is so close to 1. As you start to move faster and faster, the gamma values start to increase. And if we plugged in a number even bigger than this, like 0.999 c, you would see this number would be much higher, or 0.9999 c. So if we get closer and closer to the speed of light, this value would go up and up and up. So the values for gamma are always going to be between 1 for objects that basically are not moving any significant amount of speed of light, and they're going to go up as high as we want as we approach the speed of light. So basically the values you're going to get are between 1 and sort of infinity. All right? Let's do one more example. And this is another good one for you to pause the video and try yourself. I'm gonna let you try that, and then when you unpause, I will show you the solution to the problem. So try it yourself, pause here, and then unpause to see the answer. So here we go. Here's the answer. So remember, we can calculate the momentum, which we'll call the stationary momentum, using the equation we've used in this course, and that's 9 times 10 to the 10 kilogram meters per second. But then to find the relativistic momentum, we need to multiply by gamma, right? So we calculate gamma as 1.0328 to find the final relativistic momentum as 9.3 times 10 to the 10, which is just a little bit bigger than our stationary momentum. So there it is.